All right, let's dive right in. Today we are going to explore the hidden world of acoustics, the basic physics behind every single sound you hear, and more importantly, how it becomes one of the most powerful tools we have in medicine.
So get this. What if I told you that the key to diagnosing a really complex middle ear problem wasn't buried in some dense medical textbook, but was actually hiding in the simple physics of a playground swing? I know, it sounds a little crazy, but trust me, by the end of this, you'll see exactly how the motion of a swing can reveal what's happening deep inside the human ear.
So how on earth can a swing set explain ear disease? Well, the answer starts with understanding the most fundamental secret of sound itself.
I mean, think about it. Every sound you've ever heard, from the quietest whisper to a loud crack of thunder, it all begins with one simple thing: movement. But it's a very specific kind of movement that we care about.
That special kind of movement, we call it vibration. And the absolute best way to picture it is to go right back to that swing set. You know how it works? It starts at rest, you give it a push, it swings out to its highest point, pauses for a split second, and swings right back. That simple back-and-forth rhythm is the blueprint for every single sound in the universe.
Now, of course, not all vibrations are the same. So let's take a look at the different ways our swing can, well, dance.
On the one hand, you have what's called free vibration. This is super intuitive. It's when you give a swing one good push and then just let it go. It moves on its own, but we all know what happens next. It slows down and eventually stops. On the other hand, we have forced vibration. This is when someone stands there and keeps pushing the swing. As long as that external push keeps coming, the motion just keeps on going.
So why does that swing eventually stop on its own? The answer is a really cool concept called damping. As the swing moves back and forth through the air, it creates friction. That friction actually converts the energy of motion into a tiny bit of heat, which causes the swing to gradually lose momentum and come to a stop.
And this damping can happen at different speeds. First up, you've got light damping. That's our swing in the park, just slowly and gradually coming to a rest. In the middle, there's heavy damping. For this, imagine trying to swing through water instead of air. It would stop much, much faster. And finally, you get to critically damped. This would be like trying to swing through thick mud. The motion stops almost immediately before it can even finish one single cycle. Okay, so we've got a handle on the physical motion. Now let's figure out how we can actually visualize it. We're going to translate the swing's dance into the official language of sound, the wave.
The purest, cleanest form of vibration, like the perfect tone from a tuning fork, is called simple harmonic motion. And when we draw that motion out over time, we get this beautiful, classic shape that you see here, the sine wave. It is the visual signature of a pure tone.
And to understand this wave, we only need a few key terms. First, a cycle. That's just one complete back and forth motion. The period is just the amount of time it takes for one of those cycles to happen. The amplitude is the size of the wave. Think of it as how high the swing is going. And finally, frequency is just how many of those cycles happen in 1 second. A high-frequency wave has a lot of cycles packed into the same amount of time.
Now, let's talk about measuring the power of this wave. While we could just look at its highest peak, it's actually much more useful to know its average power over time. That's where this number, 0.707, comes in. It helps us calculate what's called the root mean square, or RMS amplitude. You can just think of it as a more practical, average measure of the wave's strength. And this isn't just some math equation. It's an absolutely crucial value that audiologists use every single day to accurately measure sound and calibrate things like hearing aids.
So, let's head back to our swing. We understand what amplitude is now. That's how high we push it. But what determines its frequency? You know, how fast it swings back and forth.
Well, it really comes down to three things. First is length. A swing with long chains is going to swing slower than one with short chains. That makes sense. Second is mass. A heavier person on the swing will cause it to swing slower at a lower frequency. And third is stiffness. Now this one's interesting. A stiffer, less flexible system will actually vibrate faster at a higher frequency. Remember that one. It's really, really important. So you take these three factors and they combine to give every single object something called a resonant frequency. This is its natural sweet spot, the frequency at which it just wants to vibrate. When you push a swing at its resonant frequency, you barely have to touch it to make it go higher and higher. And that's the magic of it. It allows us to diagnose things we can't possibly see.
Okay, so we've pretty much mastered a single wave. But in the real world, things are a lot messier. Waves are constantly meeting and interacting with each other.
So what happens then?
It all comes down to timing, which we call phase. The easiest way to think of it is as the starting position of the swing. If two swings start their push at the exact same moment, we say they are in phase. If one starts a little later than the other, they are out of phase.
And this is where one of the coolest phenomena in all of acoustics happens. When two identical sound waves are perfectly out of phase, that means the peak of one wave lines up perfectly with the trough or the bottom of the other. They completely cancel each other out. The result? Total silence. Two sounds creating no sound at all. Amazing.
But if the frequencies are just slightly different, something else happens. You hear this pulsing, a wah-wah-wah sound. We call those beats, and the number of beats you hear per second is simply the difference between those two frequencies.
Okay, we have covered a lot of ground. Swings, waves, frequency, resonance. But now we get to the payoff, the whole reason we started this journey. How does all of this physics connect back to diagnosing what's happening inside a patient's ear? Let's bring it all together.
This quote just says it perfectly. We're about to use every concept we've talked about, stiffness, mass, and frequency, as a real-life medical instrument.
And this slide shows you exactly how. The middle ear is a mechanical system, just like our swing. In a condition called otosclerosis, those tiny bones in the ear get really rigid. This increases the system's stiffness. And what did we learn about stiffness? More stiffness means a higher resonant frequency. Now look at the opposite problem, ossicular discontinuity. That's a break in that little chain of bones. This decreases the stiffness, which in turn, you guessed it, lowers the system's resonant frequency.
This is exactly why an audiologist uses a tuning fork. By presenting a pure tone, they're essentially pushing the swing. How the patient's auditory system responds, how it vibrates back, tells them about its physical properties, like its stiffness. They are using sound to measure the physics of the middle ear and diagnose a problem they could never, ever see with their own eyes.
So we started with a simple swing and we ended up deep inside the human ear. It just goes to show you how these fundamental laws of physics give us a powerful lens to see the invisible. Which leaves us with one last thought. What other secrets, hidden deep within the human body, are just waiting to be understood if only we learn how to listen to their vibrations?